This is Lab 3 on magnetic field of permanent dipole magnets. In this lab, the main goal was to become familiar with the idea of magnetic field, particularly the one of a dipole magnet. Another goal was to understand the distance dependence of the magnetic field to a small bar magnet and compare those values to the distance dependence predicted by the equation for the on and off axis magnetic fields. In this lab, we use the Biot-Savart law. Using the general equation, the magnetic field of a bar magnet is K times R to the N, where K is just a bunch of constants and R is the distance from the bar magnet to the magnetometer, and N is the value that we find in this lab. Then the superposition, since on the magnetometer we're acting the magnetic north field and the bar field, we have to cancel out the magnetic north field in order to calculate only the magnetic field of the bar magnet. When the magnetometer is far away from the magnet, it measures a near zero magnetic field in the x direction. As the magnetometer moves closer to the magnet, the x component will increase. Since I did this lab in Italy, the theoretical value of B net is 47.712 microtesla, and I work with a value of 47.3 microtesla. First, we have to find the magnetometer chip on our smartphone in order to measure the exact distance from the bar magnet to the specific point by positioning the phone at certain distances so that the x component in one position and the y component in another position were at their maximum. And then we have to observe the value of Bx, By, and Bz from the magnetometer when it was 45 degrees off axis. Here, the perp is the distance at which the magnitude of B net is 100 microtesla. Here are the values that are recorded. The purpose is to measure the distance of the smartphone from the bar magnet in order to have the magnitude of B net at 20, 70, 120, 170, and 220 microtesla. I did three trials for each of these distances, and the blue cells represent the averages of the distance and the Ex. Here is the graph from the previous values. As we can see, since it was hard to plot the magnitude of B bar versus the distance, we plot natural log of Bx versus natural log of the distance, and we find out that N is the slope of this line, so negative 0.71114, and K, ln of K is 4.9601, which is the intersect of the line. To calculate U for the computational model, we got the value from the relation of K with mu, and we found out that mu is 32.99, and K could be calculated from the graph since ln of K was the intercept of the equation of the line. Here are the values of the off-axis. In the first column is the distance on-axis for the bar magnet. The second column represents the By earth, so the y component from our magnetometer up at on-axis position. The third column calculates the distance from the bar magnet at 45 degrees from the axis. Bx, By, and Bz are the values of the magnetic field recorded at 45 degrees from axis. By corrected is calculated by adding By earth and By. And the last column calculates B net from Bx, By corrected, and Bz. Here's the computational model. First I write the constants, then I calculate the magnet and the mu value, then I create a function in order to calculate the magnetic field. Then I wrote all the obfuscation vectors for the magnetic field of the bar magnet. Here I created 2 arrows that are on axis and 4 that are perpendicular to the bar magnet, and then I created 8 arrows that are 45 degrees from the bar from the axis of the bar magnet. And here's what I got. The 2 orange arrows are the magnetic fields on axis, the 4 cyan arrows are the perpendicular on axis, and the 8 green arrows are 45 degrees different spot on space of the bar magnet. Here our value of N is negative, so negative 0.7114, as we expected since the magnetic field decreases as the distance from the bar magnet increases. In fact, the magnetic field of P net is equal to K times R to the N. Our value mu result will be 32.99. From the magnitudes calculated by the computational model, we can see that B field on axis has the greatest magnitude compared to B field perpendicular and 45 degrees from axis. If you didn't consider the magnetic north, we'll probably have a lower value since it will be exactly on the axis. And if we stick two identical magnets together end to end, the magnetic field will double.